Hello, everyone. Welcome to our research talk today. I'm going to let everyone join us and give maybe one more minute just so that we can make sure everyone can hear us and see us. So I hope you can also see our screen. Today I'm joined by Dr. Walt Charzenko and Cheryl Kung. And Dr. Walt is one of our professors here, and he has a master's and PhD in electrical engineering from the University of Colorado Boulder. And he's been working in industry for over 35 years at companies and laboratories such as Philips, ECG, NIST Boulder, Boeing, and Eospace. I'm also going to give them a little time to introduce themselves as well. And Cheryl is one of our Masters of Science in Electrical Engineering students, and she currently works at Amazon. And I will give it over to them to really go into depth, but please keep in mind, you can ask questions by putting your questions in the chat or even raising your hand if you would like some clarification on any of these slides in depth. So Dr. Walt, Cheryl, let me give it to you guys to take it away.
Okay, thank you. So I want to introduce this talk. I was given the opportunity, Cheryl was taking a class for me last autumn, I believe, or last winter actually it was, previous winter. And she approached me on a topic. She was interested in working on antennas for satellite systems, similar to the work she's doing. And this really kind of struck a good chord with me. My own background was about 20 years ago, I was working on something called the Teledesic program. And it was the first attempt to bring global internet to the entire Earth, which was a consortium of Boeing, Motorola, and Hughes aircraft. And actually what happened is during the middle of the program, I was working on the phased array antenna systems that were going into the satellites. I jumped ship and joined Eospace and developed the first generation of 40 gigabit per second modulators, which went into the fiber optic networks. So back then there was a competition between the satellite systems and the fiber optic networks. The fiber optic networks got installed, and since that time they've been the dominant medium in global internet traffic. That's because of their bandwidth having basically terabits per second of information transferred over single mode fibers. But since that time, we've had several billionaires have made their money on the internet, using the internet, the global fiber optic internet, and they've reinvested that money just recently into prominent space programs, both SpaceX and Amazon's program as well. And part of the reason they invested in the space programs was to resuscitate this idea of a global internet that could be run through low Earth orbit satellites. So that's kind of the justification for the talk. And what I wanted to present was Cheryl's been working in independent studying basically antenna theory, applications of antenna theory, and characteristics of antennas, and then learning the software you need to handle to do modern antenna design. And she's picked a very interesting problem. It goes dear to my heart. It's trying to get some phased array antenna systems, except it's even more aggressive now that they're trying to take the satellites that we were trying to do and place the antennas here on the ground. So let me go ahead and introduce Cheryl. She's an antenna engineer working on the Kuiper program at Amazon. And go ahead and take it away, Sharon.
Yeah. Hi, everyone. I'm Cheryl, as Dr. Charzenko and Dina mentioned. So right now I'm an antenna engineer. I'm getting my master's in electrical engineering at UW-Bothell. I got my bachelor's in engineering at UC Davis in 2017. And since then, I've been an RF test engineer working in the aerospace industry. I've worked at quite a few different companies, SSL, SpaceX, Tethers Unlimited. And right now I'm an antenna engineer at Amazon's Project Kuiper, which is their LEO satellite internet constellation initiative. And specifically, I work on the antenna technology and innovations team, which designs the phased array antennas for the satellite and the ground customer terminals. So yeah, I'm really excited about this talk. I've heard about phased array antennas when I was an intern at SpaceX, and it's been something that I've really wanted to explore for a long time. So I'm really glad I get the opportunity to do so. So for my talk today, I'm going to talk about internet satellites in general, why they're useful, the different types, why phased array antennas are so important for them. And then we'll get into more specifics about antennas and single antenna elements, what performance metrics we're going to look at, and then how we design those antenna elements around the satellite constellation, different types of antennas that we can use, and then more on current research about how 3D printing, the technology has advanced far enough that we can actually use it to build really cool, complicated phased arrays. All right. So why do we need internet constellations in the first place? I think everyone here is using the internet right now to join this talk. It seems like it's everywhere, but it's not really. And in the US, it's actually missing in a lot of places, as you can see on the map there. And trying to get fiber out there to these places is pretty expensive. It's about over 100 grand per mile to lay it out, which makes sense in really dense cities, but not so much in like the rural areas where there might be one person per 10 square miles. And if we look at the global scale of it, it's actually quite severe. There's about 2.9 billion people who are offline right now, and 96% live in developing countries. So as the internet becomes more crucial for education and jobs, the lack of internet connection can lead to increased inequality across the US and the world. Fiber optics isn't the most efficient and cost-effective way to get it out, which is why internet satellite constellations may help a lot of these underserved communities. So there's a lot of different types of internet satellites. When I was at SSL, I actually worked on geosynchronous internet satellites. They're really great because they are stationary over one part of the Earth. They can cover a huge area, and they're relatively simple to design. They use like a bent pipe system, which will take data from one sector of the Earth and then bring it to another area. But the only problem with geosatellites is that they're actually have to be really, really far away. As you can see on this graph on the left, they're 36,000 kilometers away, which actually does increase latency quite a bit for data. So it is more like on DSL levels where it's like really good geosatellite internet is about 5 megabits per second. And this is why LEO is really important. LEO is really close to Earth comparatively. It's on the order of 6,000 times closer, or 600 times closer with, or 60 times closer with the Kuiper system that I work on at work, hovering around 600 kilometers. And that really decreases latency, but it also creates other problems because for a satellite to stay in LEO orbit, they have to travel about 17,000 miles per hour, which means you need an antenna that can scan across the whole horizon to maintain a signal. And that's where phased array antennas come in. Phased array antennas are electronically steered. They're much faster than mechanically steered antennas, and it's very important to use them for both on the satellite and on the ground customer terminals. All right, so more about phased array antennas. Phased array antennas are actually an array of antenna elements where each antenna element has a variable phase and amplitude. And by offsetting the phases of adjacent antennas, as you can see in like the first photo to the left, you can create a combined beam that points in a certain direction. So in the photo to the left, the antenna elements on the top are a little bit more delayed than the antennas on the bottom, which cause a shift in the beam of an angle of theta. The other cool thing about phased array antennas is that they can actually create multiple beams. So you can track more than just one satellite, which is really useful in a satellite constellation. And these antennas have to be really low cost because they have to be affordable for a user. Currently, a lot of phased array antennas costs on the scale of thousands of dollars. And it's to make it achievable, we have to make them on the order of hundreds of dollars. Okay. Now that we've gone a little farther into complex antenna theory, let's go back and talk about what antenna actually is. And they're basically just transition devices from transmission lines into free space energy waves. Oops. Sec. Right. And there are a lot of different types of antennas. The more traditional ones, the dish ones that people use for like television, or like you see a lot of them for deep space signals. They have reflectors in them that concentrate a signal around a feed source. Another one that is really, really simple that I've used actually a lot before is a wire probe antenna. And these are just a wire soldered to a coax cable. So they're sometimes called sniffer probes because they can find electromagnetic interference on circuit boards when they're not wanted. And then there are also the antennas that you see on cell towers. They look like flat panels, and these are actually also phased array antennas. And they're used for focusing the antenna energy on the ground where all the users are, and not up at the sky where there's no one. So there's a lot of ways to describe antenna performance. These are the main ones that we're going to talk about today. It can be a little confusing because antennas are actually passive devices, but we describe them using antenna gain. And antennas are also reciprocal, which means they can transmit and receive. So I'm going to talk about these performance metrics as if the antenna is a transmitter, but they also apply as a receiver. So the first metric is directivity. Directivity generally is how much power is concentrated by the antenna in a specific direction. And directivity is usually compared to an isotropic pattern, which is a pattern that radiates power equally in all directions. So an antenna with high directivity radiates better in one direction than all over. The other metric is radiation efficiency. Radiation efficiency is the ratio of how much of the radiated power or how much power is actually radiated from the antenna compared to the power that was inputted into the antenna. And then antenna gain is directivity times efficiency. So for the antennas that I want to design for satellites, we really want something that has high antenna gain. The better the antenna gain per element, the less antenna elements that we potentially need for a phased array, which can lower the cost significantly. The other important metric to talk about for antennas is polarization. So polarization technically is the pattern the electric field vector cycles through in the plane perpendicular to the propagation direction, which is a little bit of a weird concept to think about because you have to think about electric fields in 3D and how they move outward. But the main point about polarization is that it's important that the transmitting and receiving antennas have the same type, so that you don't get any losses associated with it. And different antennas polarize in different ways, so this factors into what antenna element we end up choosing. So now that we've talked about antennas, we have to talk about the LEO satellite that we're trying to design a customer terminal antenna for. So since I work at Amazon Kuiper, I'm going to talk about their systems. So They have 3 orbital shells around 600 kilometers. Their orbit speed is about 17,000 miles per hour, which gives them about a 2 to 20 minute visibility. So the antennas do have to scan pretty fast. And they're working at quite a high frequency rate for standard aerospace operations. Ku to Ka band, which is just aerospace speak for 17 to 40 gigahertz. And higher frequency is really good for higher data rate. You're targeting quite high speeds of up to 1 gigabits per second. And the other bit is that they're also circularly polarized. And this is just a general assumption because almost all satellites that project towards Earth have to be circularly polarized due to alignment issues. And we'll get into that later. So all of those factors that I just talked about in Amazon systems funnel into something called a link budget. And link budget is where you determine how much power is actually going to hit your receiver on the Earth. And this will tell you exactly how much antenna gain your antenna will need. And it really just boils down to this transmission formula, Fries's transmission formula. The biggest part that affects it is r squared, which is the radius of, or r squared is the distance between your transmitting and your receiving antenna. So the farther it is, the lower the power you'll end up receiving. Same thing for frequency. So lambda here represents the wavelength of the frequency. So the smaller your wavelength, i.e. the higher your frequency, it'll actually increase the amount of power received. So that's another reason why, this is the mathematical reason why LEO satellites are actually really effective. So for a LEO system that's operating around 600 kilometers versus a GEO system that's operating around 36,000 kilometers up, you get a gain of about 3,600. And then if you're comparing frequencies, if you're using a frequency that's about 1 gigahertz versus something that's around 30 gigahertz to transmit your signal, you get about a 900 times difference. One of the big things that factors into that link budget is polarization loss factor. So the polarization loss factor has to deal with what I said before about the alignment between your transmitter and your receive antenna. So two of the main ones that are usually used are linear and circular. This is just justification for why a circular polarization is the best for aerospace and satellite communications. Because you don't really know what alignment your antennas are when they're crossing each other. You're not linearly polarized isn't a great choice. So as you get more and more misaligned, i.e. that your angle becomes more closer to 90 degrees, you can actually lose quite a bit of your signal. But if you're circularly polarized, when the antennas are directly facing each other, you won't have a polarization loss. There is some issues because when you're actually looking at a satellite from the ground, the satellite is moving, so you won't actually have a perfect alignment every time. But even so, having a circularly polarized antenna does decrease the amount of loss you're going to suffer from polarization. So that's a really important factor when deciding on what antenna element to use. So one of the really common antenna elements that are used for phased array right now are planar microstrip antennas. They're really popular because they're very easy for mass production. They use printed circuit board technology. And a lot of them actually look like 2-layer PCBs. So planar microstrip antennas, they consist of a radiating patch. So this square section on this picture right here. And then a feed structure. So what gets the signal to that radiating patch, which is just this microstrip line over here, a dielectric, and then a ground plane. This is one that I threw up in a antenna simulation model of CST, and I only got about 4.6 dBi of directivity, which is a little bit low for a rectangular patch antenna. They can actually get about 7 to 9 dB per element, but that's still not super high compared to a lot of different other antennas, which we'll get into later. There are a lot of reasons why they're currently used right now. Actually, the photo to the right is from a Starlink customer terminal from SpaceX's internet satellite constellation. They're using circularly polarized patch antennas. But if you want to tune the performance of these, they're actually pretty hard to do. There's not a lot of wiggle room. The only things you can really control is the patch size, radiate the feed structure, how well its impedance matched to the patch, the substrate you use, the dielectric substrate, and the size of the ground plane. So that's why there's not too many ways to improve that gain. It's very limited to that 7 to 9 dB. But one of the interesting ways that people have gotten around that 7 to 9 dB is that they stack patch antennas on top of each other, essentially turning them into 3D antennas. And that can increase gain by quite a bit as well. So that kind of is reason why we want to look at 3D antenna structures. And one really interesting one is helical antennas. Helical antennas are pretty much what they sound like. They're just, at its simplest, they're just wire that's been turned around some sort of structure. And there's a lot of ways to adjust performance for these, and they can get up to 15 to 20 dB of gain, which is much more than a planar microstrip antenna. And they're also naturally circularly polarized, and there's a lot of ways to adjust that. So you can have a pretty good axial ratio, which means that your polarization stays as circular as possible and doesn't get too distorted when you're trying to transmit through the atmosphere. But the reason why these helical antennas aren't really used is because they're not really mechanically sturdy. They have to have a lot of supporting equipment, or they have to be used in environments that aren't severe. So as you can see in the picture on the top, there's a mechanical structure that the antenna is wrapped around. And on the figure on the bottom, talks about several different ways that people use to support these helical antennas, either wrapping them around a certain dielectric, inserting rods around them. And they're also, in addition to not being that sturdy, they're also pretty difficult to manufacture at high volume. These helical antennas have to have very precise turns, very precise spacing to get the performance that you really want. So most of the ways that they're manufactured is with expensive machining tools. In addition to helical antennas, there's a bunch of research right now out for other different types of phased array structures. So a couple that I've looked into use something called direct metal laser sintering, which is basically you're welding metal powder together to create a metal structure. And a lot of these target wideband uses. So like the Vivaldis on the left, they're, oops, the Vivaldis on the left, those are made using direct metal laser sintering, and I believe they were investigating not only the printing process, but also using a unique array alignment outside of standard array, like egg carton alignment, to see if that improves performance. Another one that also uses DMLS was a high gain wideband waveguide. So this more focused on integrating the feed structure into an antenna. One of the ways that influences antenna loss is how well your feed structure is matched into your antenna. If it isn't matched super well, you can get a lot of reflections and therefore a lot of loss that way. So this kind of creates a really cool, precise way of integrating that into an array. And another one that actually doesn't use direct metal laser sintering is this machined frequency scaled ultra wide spectrum element. It's actually a completely new type of array that was designed mainly to be easy to machine. And there's a lot of interesting performance associated with that as well. But a lot of these are all about printing with metal or using metal or machining metal. And I wanted to explore something a little bit different with new technology that's coming out from Rogers Corporation. So what I'm proposing for my thesis is to use this 3D printed dielectric material from Rogers. It's called Radix. And it actually works on a pretty wide frequency range from 10 to 24 gigahertz. And you can print a dielectric shape that you can wrap around antennas with, like helical antennas. So for example, one type of antenna that they've manufactured with kind of not with 3D printed dielectric, but cone-shaped dielectrics is this conical spiral antenna. And how they did it was they machined a planar spiral and then extended it over the structure. You can do something similar except with this dielectric material and maybe make it into other interesting shapes. Yeah, that kind of covers most of my talk.
Did anyone have any questions for Cheryl or Dr. Walt? Did you want to add anything? I don't see any questions in the chat. Oh, Dr. Walt, yeah, go ahead and unmute yourself.
Sure. So, Cheryl, I don't know if you've got the slide there handy, but I think you wanted to show what you're proposing for your master's dissertation. You're going to take a look at this guy and then propose building some prototypes. Did you want to share that slide on the potential master's dissertation?
Is it not this slide?
Oh, I thought there was a, okay, maybe it was this slide. Okay, my bad. Go ahead, I'll open up the floor to, I'm sure there's some students out there that are curious to this field.
Cheryl, have you completed your coursework? Have you taken most of your electives and advanced topic classes?
Yes.
Okay, great. So if anyone has questions about school too, Cheryl's got answers for you. I do
Actually, I had a question about both the manufacturing side of it and the technical perspective of it. So something that you talked about in the beginning was phased arrays, which I didn't realize they were expensive. I know they're used a lot in like medical imaging technology, like ultrasound. So as part of your like proposal for your master's to minimize the cost of this, or is it mostly just trying to find a better route of this antenna technology and then minimizing the cost of it?
It's mostly cost driven, while trying not to lose performance with it, because in order to achieve the performance that we currently need
Mhm.
to close links on satellites, so a lot of it uses these planar microstrip antennas, and they have to use a lot of them. And when you use like a really large array, they can get pretty expensive. And so that's why a huge part of this is looking at kind of novel antenna elements that we can maybe use to reduce the size and therefore the manufacturing costs of the array itself.
I guess I wanted to add one thing to that. When you're developing arrays for ultrasonic applications, say medical applications and whatnot, those are at what RF people would call very, very low frequencies. those are like at circuit frequencies. These types of antennas are used in what's known as millimeter wave systems. So they're up around 30 or 40 gigahertz. It gets exponentially more expensive to build something that works at millimeter wave frequencies as opposed to something that works in the megahertz region. So that's where the cost comes from. These are, to give you an example, the phased array antennas that Cheryl is talking about, when we first proposed them to turn them from the military marketplace and put them on satellites, they were running at about $1 million to $2 million a piece on military marketplace. And to get them on a satellite, we had to bring the cost down to approximately $100 per element. And the number of elements were thousands. So that was no mean feat to get the electronics to work at those frequencies, foundries. There was a lot of technology that went to it. And that's about as far as we went. Now, here we are 20 years later, the technology has moved even further forward. And so something like Cheryl is proposing is actually a 3D antenna, phased array antenna that can be mounted on the ground and sold for several $100s, including all the electronics inside. It's just, I think that's phenomenal. I mean, it's been, for me, it's been really eye-opening to see what's happened in the last 10 years. But the main difference is frequency, you know, where they're used, the frequencies they're used at.
Got it. Thank you.
Mhm.
And
Yeah.
great presentation. Congratulations. This is super really cool.
Yeah.
Yeah, thank you.
I see Jacob has his hand up. Jacob, do you want to unmute yourself and ask your question?
Yeah, thank you. Can you go to the very last slide real quick?
Sure.
So I think I have a couple of questions here. I suppose first off, have you been able to like build this antenna in like Keysight ADS or any sort of like simulation software and see like what its how its performance is?
Not yet. I haven't had a chance to work with that software.
Okay. And then so you were saying, so this antenna that you're proposing here, are these, so this element itself is not a phased array antenna, but you could hypothetically use multiple ones of these as a phased array antenna, correct?
Yep.
Okay. And then so just from my curiosity, because I work for T-Mobile, so I work in the telecom industry, and I see like the frequencies you guys are using we're currently working with SpaceX to do like something very similar to this with, you know, just normal people's phones. And something that we've kind of been running into is you know, in our simulations in the lab is at these, you know, even at the lower, you know, I think we're providing spectrum in like the 2.1 gigahertz range, and we're already seeing some kind of interesting effects when like certain weather patterns come in. So I'm just curious because you have experience in like the aerospace field, like how much does like weather impact your path losses at, you guys are using, 10 to, I see on here 10, 24, you said going up all the way to like 40 gigahertz.
Yeah. So actually with higher frequency, you tend to get less atmospheric issues. I know
Really?
there's like certain frequencies where it will kind of resonate with like water molecules in the atmosphere. So they tend to avoid those. And also the polarization does help quite a bit with circular polarization. You tend to get a little bit less of the effects.
That's interesting. Is it, so you don't get like scattering, like especially at those high frequencies? I figured, you could get RF scattering off of the clouds. That doesn't happen as much.
I can't say for sure,
Okay.
but it is basically just trying to avoid the frequencies that resonate with water and things that are in the air a lot of the times. And
Gotcha.
with higher frequency, you do get a little bit more power as well. So
Sure. Do you foresee going, are there any issues going higher than 40 gigahertz? I know in a lot of the talks that we have with like Ericsson, Nokia, 6G's pretty far away, but they're talking about going from like 100 gigahertz all the way into like the terahertz frequencies. Is that something that's even possible with this kind of application?
I don't know if the challenge would be in the antenna itself or in more of the systems that have to process it, because once you get into the higher frequency, it starts to have weird effects performing on, let's say, the circuitry inside the antennas, like the digital
Sure.
inputs.
And things like that. And
Yeah.
also, we don't really have clocks that operate at that high yet, from my understanding either.
Yeah, there would probably be new resonance effects and things like that that you would see in your like circuit board functions.
Myself, I was going to add something to Cheryl's talk. Having worked at those frequencies myself for a number of years, up through 150 gigahertz, I do know there's atmospheric, basically blockage zones that's used in communications out at 60 gigahertz and whatnot. So that's why some communications takes place in some secure channels at 50 gigahertz, and then they frequency hop between 50 and 60. But the major issue is if you look at most of the satellite systems that are in orbit right now, LEOS orbits, they are using the KU band. And I think what's a little bit different, which is a little bit lower than the KA band. And so Kuiper is set to work at 30 gigahertz, if I'm not mistaken. To move to higher frequencies, I think it's mostly shorter distance things like automotive radar that they're proposing planar antennas to work on the sides of automobiles, but obviously they don't have to go out for 600 miles to see something. And then once you move up to real high frequencies, the electronics, if it's available, and everything else becomes very, very, very expensive. I used to sell components into that market that would cost about $10,000 each. So it's kind of a cost, and as you go up in higher frequencies, and also performance issues that come into play, I think. But 30 gigahertz is pretty good. It's been proven in satellite technology. It's currently in use on a lot of satellite systems.
Gotcha. That's good to know.
Yeah.
All right, we have some other questions in the chat. So from Shalene, in your current project, Cheryl, in Amazon, is there an incorporation of the satellites with VSATs in rural areas?
I don't think I'm familiar with VSATs. Could you explain that?
I definitely cannot, but I will hold tight and ask that question. If you have a second, if you could elaborate in the chat. We also have a question from Sarah. Great presentation. What are some of the interesting finds you discovered in your research of other antennas, satellites, and why did you select this as your thesis topic?
In terms of interesting things I found, a lot of it is just kind of how simple and complicated antennas are. Like, in essence, anything can be an antenna if it's like, the basics of an antenna is that you have a time varying current. So really simple things can be antennas. And so that's why there's just so many different types of antenna elements out there to look at and to research. And there's been a lot of research into really unique shaped antennas, but not a lot into how they're manufactured. And I think that's kind of what I've noticed in my research. And yeah, in terms of why I selected the thesis topic, I just really enjoyed applied physics, and antennas are pretty much as close as you're going to get to that in terms of electrical engineering.
Cool. All right. So we have another question. What's the time frame look like to build one of the antennas you're proposing?
So the time frame that I'm looking at is that we're going to focus on building just one antenna element for the next couple months. And then after that, we're going to do a lot of analysis on that element, see what kind of gain we're getting, what kind of beam pattern that it produces, and kind of just choose what type of antenna element we want to build a phased array from. And then hopefully we'll have a completed phased array by the end of winter quarter next year.
Great. Well, does anyone else have any questions or anything they wanted to add?
I just wanted to thank Cheryl for her talk, but also I wanted to say that you are using CST for this. You have your employer has graciously offered the ability to use CST in all your modeling, and a big part of your study was to get up to speed on using CST because these are fairly complicated elements, and you can see that the materials themselves have to do with the modeling as well, like these new materials available from Rogers. How we're going to do the conductors, we've got some ideas on that. So there's a lot of work in just making the individual antenna element, characterizing it, and see if we can lower its cost. And when you propose making a full-scale array, I think we should probably, that would be a little bit ambitious for a graduate master's thesis.
I should specify that it's a sub-array.
Yeah, we're looking at making a prototype, basically, you know, some sort of demonstration. It's not going to be 1,000 elements, you know, I can guarantee that, you know, but something that would be on a subarray size that we could demonstrate. And we're just looking at the antenna elements themselves. We're not even looking, perhaps, unless we're looking for testing purposes, we're not looking at the feed networks or the basically the phase shifters and beam formers. It's the electronics.
Yeah, there's a lot that goes into a phased array in terms of, like, you know, the electronics that generate signals, and a lot of DSP that goes into it as well. To kind of simplify this, we are definitely removing a lot of it and really just focusing on that physical antenna structure.
I have a kind of like general phased array question because I'm not too familiar with them. Can you explain on the slide, like one of the beginning slides, can you explain how the theta in the phased array antenna changes, like when it's in use? Is it software driven or?
It's mostly software driven. There are usually things called either digital phase shifters or digital beam formers that essentially add some sort of phase delay into the each antenna element.
Gotcha. Okay, cool. Thank you.
We have a couple more questions in the chat. So one is, do you have a plan on how these will be implemented into the field post development and testing?
I don't know how to implement it. I do have a couple ideas based on just like how we use them at work and stuff, but I don't know if these will necessarily go into, you know, customer terminals or satellites even, but they do have a lot of potential as probes or other kind of testing metrics, because another part of designing antennas is that you have to be able to test them, and designing test probes are actually pretty complicated. But another side effect of using that could be in testing instead. And for how long it takes to characterize, it can be pretty quick for a small array. So usually you're using an anechoic chamber and you're just scanning the beam pattern that you get from your antenna. So that, depending on the size, it can take, you know, a whole day or just like, 10 minutes. That's why we're building a really small subarray. We're not going to actually build a huge panel. Subarrays are a lot quicker to characterize. And a lot of that characterization is also done by computer processing. So just calculating other things like other antenna metrics like beam pattern, your axial ratio, other stuff that I didn't want to mention because they can get a little bit complicated when you get into it. But yeah, there's 2 parts of testing: capturing the beam pattern and then processing that.
Great. Thank you, Cheryl. And thank you for taking us through this and explaining it so carefully. I think I also might have somewhat of a handle on it. So thank you. We really appreciate it. Dr. Walt or Cheryl, did you have anything you'd like to add before we say good evening to everybody?
I'd just like to thank Cheryl also. I think she's done a lot of work and a lot of good work, and I just wanted to give her a hand clap. Thanks for the talk, Cheryl.
Yeah, thank you for the support. I really do appreciate it.
Mm-hmm.
And if anyone has any questions, please feel free to reach out to our office. We're always happy to answer and connect you with anyone you heard from today.